Today is 5.1 differential equations and slope fields. We've kind of talked a little bit about differential equations when we did Euler's method. Basically, you have an equation that has x and y and possible derivatives of y. So a function y equals f of x is some solution to this differential equation if the equation is satisfied when y and its derivatives are replaced by f of x and its derivatives. You're probably thinking like, what are you talking about? A perfect example of a differential equation, the Euler's method equation we had the other day was, it was y prime is equal to x minus y. This is an equation of x and y and its derivatives, okay? I could also have something like x plus y prime plus y double prime is equal to 3x squared. This is also considered a differential equation because it has possible derivatives of y in place of it. We did this a lot also when we would have, when we did implicit differentiation, x squared plus y squared is equal to like xy, and then I had to take the derivative of this, so I would have like 2x plus y, 2y dy dx. Oh, of course I gave myself a product rule problem, so y plus x dy dx. So this would be another example of a differential equation because this comes up with x and y and possible derivatives of y. So what we're going to do today is, let's say we had some of these differential equations and I wanted to find the solution. Like I wanted to figure out what value or what equation for y makes this statement true, or what value for y in y double prime would make this statement true. Those would be solutions to my differential equations. Okay? So first, let's just start off by verifying. Okay? I want you to determine whether each of the following functions is a solution to the differential equation y double prime minus y is equal to 0. Well, my first potential solution is y is equal to the sine of x. Well, in my equation, I have my second derivative and the original function. So before I plug anything in, I'm going to go ahead and start by finding what the second derivative is. So if y is equal to the sine of x, that means y prime is equal to cosine x, and y double prime would be negative sine x. So I'm going to plug in this guy and this guy and this guy over here and see if I get a true statement. So y double prime was negative sine of x minus y, which was sine of x, is that equal to 0? So I've got negative sine x minus sine x question mark equals, well, that's negative 2 sine x equals 0. Now I could find a specific x value where that is true, but overall I wanted to plug in y and get a true statement at all points of x, not just one. So this is not true. So this one is not a solution. Okay. At any point, if you want to try the next two on your own before I get to them, go ahead and pause the video, give it a try, and then push play and come right back. Okay. Well, now I have y equals 4e to the negative x. Maybe that one's a solution. So again, start by finding y prime. So negative 4e to the negative x, and y double prime would be negative times the negative, so actually positive 4e to the negative x. I plug that in, and I'm going to have 4e to the negative x, because that's y double prime, minus y 4e to the x is equal to 0. Those two things do cancel each other out, and so this works. Okay, so this is a solution. So y equals 4e to the negative x is a solution to y minus y double, it's y double prime minus y. Y double prime minus y equals 0. Basically, y double prime, the second derivative, has to be the exact same thing as the original function for this to work. Y equals c e to the x here. Well, what does c mean? Well, c is just a constant. We don't know what it is, but that's our constant of integration that has resulted from whatever we've done up to this point. So y prime is c e to the x. Y double prime is c e to the x. So y double prime, so c e to the x minus c e to the x equals 0. That checks out because 0 equals 0. So yes, y equals c e to the x is a solution. No, I forgot to write the last one. Oh, no, I did. Yeah, that one is a solution to y double prime minus y equals 0. Okay? So the first one, not a solution, but parts B and C were a solution because they satisfied the original differential equation that they gave us. Okay? Well, now let's see. We've got x y prime minus 3y equals 0. I want to verify first that cx cubed is a solution, and then find the particular solution determined by the initial condition y is equal to 2 when x is equal to negative 3. This is going to help me solve for C. Okay? All right, but before I do that, I have to verify that when I plug this into here that it works. Okay? This is what we like to call a general solution, because I don't know what the value of C is. When I find the value of C, then it's going to become my particular solution. Okay? So I have xy prime minus 3y equals 0. All right. Well, I'm checking to see if y equals cx cubed is a solution. So I need y prime equals 3cx squared, right? C is treated like a constant, so you just leave it out front like you normally would. Okay? So then I'm going to plug those in over here. So x times y prime is 3cx squared minus 3 times y, which is cx cubed, equals 0. So I'm going to clean this up. 3cx cubed minus 3cx cubed equals 0. Those two things are going to cancel each other out. So yes, y equals cx cubed is a solution. Okay. Now to find the particular solution, I need to figure out when x is equal to negative 3 and y is equal to 2, what is C? So cx cubed. So 2 happens when you end up with negative 3 cubed. I plugged in the x here, my y value here. So 2 equals negative, let's see, negative 3 cubed is negative 27 times C. So C is equal to 2 over negative 27, or negative 2/27. So then my particular solution is y equals negative 2 over 27 x cubed, but that's only true when I have the initial condition that I was given. Okay, this is not true for any other, I mean, it could be true, but it's most likely not true for any other initial condition. Particular solution to xy prime minus 3y equals 0 is blah when x equals negative 3, y equals 2. Okay, if I were to change my initial condition, that would change my value of C, which would change my particular solution. Okay, let's try another type of situation here. So let's say I gave you the differential equation and I just told you to solve. I want you to solve the differential equation at 2, 9. What the, who the, where the, okay, so basically this is my equation. This is my differential equation. Okay, this right here is my initial condition. And I want to find out what is the one equation for y that would satisfy this. That if I were to plug in y here and the derivative on this side, I would end up with the true statement. Okay? So to solve these, I want you to think of, oh, there's a song out there, but the catchphrase or the catch line, I don't think it's the chorus, but like there's a pretty common phrase in the song. It's called "Keep 'em separated." I don't think the song is actually like super school appropriate. I usually just play a small clip of it. You can look it up, listen to it. Anyway, anytime you see one of these situations, you got to remember, you got to keep them separated. Okay? And I say keep them separated because you notice how I have X's and Y's kind of all mixed up, all on one side, okay? You want to keep your X's on one side and your Y's on the other side. Right now I have dy dx equals 2x over y. They're all mixed together. I want all of the Y's over here, all of the X's over here, okay? So to do this, got dy over dx equals 2x over y. The simplest way to do this on this particular problem is to simply cross multiply. Y times dy becomes y dy. Dx times 2x becomes 2x dx. Boom, done. All of my y's are over here, all of my x's are over there. So far, so good. Okay, just remember, keep them separated. Okay? All right, so from here, it's like, okay, well, what do I do now? So I want to get rid of dy and get rid of dx. The only way to do that, the only way to undo a derivative is to do what? Take the integral. But what you do to one side, you got to undo to the, what you do to one side, you got to do to the other side. So I'm going to integrate both sides. I'm going to have the integral of y dy and the integral of 2x dx. Okay? Well, the antiderivative of y dy is very simple. Y squared over 2. Now, technically, there's a plus c. I'm intentionally not going to write plus c because if I have a plus c on both sides, there's really no point because they're going to combine at some point. I'm just going to write plus c only on the side with the x. Okay? So this is going to become x squared plus c. Again, technically, we could have written a plus c on this side, but it would combine with the plus c over there. Sometimes kids, when you guys see plus c on both sides, you want to like cancel each other out. Don't do that. Okay? That's not the goal. We want to keep the plus c only on the one side. All right? So this thing right here is what we call the general solution. If I were to take this right here, I could plug this in, I could actually solve for y and plug it in up here and this equation would work, okay? But I don't want the general solution, I want the particular solution at this specific initial condition, okay? So what I'm going to do next is go ahead and plug in that initial condition, all right? So when it says y of 2 is equal to 9, 2 is your x value, 9 is your y value. So that means 9 squared over 2 is equal to 2 squared plus c. So 81 over 2 is equal to 4 plus c. So c is equal to 81 over 2, so 77 over 2. Okay? Is that right? No, it's not. Oh, it's minus. What am I doing? Not minus 4 over. I did 4 over 2. It's minus 8 over 2. 73 over 2. I wrote that one. I was like, it feels right. Maybe? Nah, it doesn't. Okay. So now I can take this. I'm going to plug it back in up here. So then y squared over 2 equals x squared plus 73 over 2. Now we are one step closer to our general solution. We are not there yet. We want to solve for y. We want to keep y. We want to get y completely by itself. Okay? So to do that, I need to multiply both sides by a 2. So y squared is equal to 2x squared plus 73. Multiplying by 2, remember, cancels everything out. Cancels the 2 out here, and then you bring it 2 there. And so then y, when I take the square root of both sides, I have to put plus and minus square root of 2x squared plus 73. Now, technically, how many equations do I have here? I have 2, because I have a plus and a minus. I only want to keep one of them. So remember, your initial condition was that when you plugged in a 2 for your x value, you got a positive 9 for your y value. So if I plug in a 2 here, the only way I'm going to get a positive 9 is if I keep only the positive radical. Okay, so then we are going to keep y equals positive root 2x squared plus 73 because that satisfies the initial condition. If they had given me the initial condition 2 negative 9, then I would have kept the negative radical instead of the positive. So you have to be careful and check that every time. Sometimes you want the positive, sometimes you want the negative. It's going to largely depend on your initial condition. Okay, so where is this taking us? What does this lead to? So the next thing, your sub, if she hasn't already given it to you or they haven't already given it to you, they will here in just a second. We are going to do what is called the Intro to Slope Fields worksheet. So you have a differential equation, okay, and then we have a whole bunch of general solutions to those. That general solution is going to change every time depending on our initial condition. Every time you have a different initial condition, it changes the solution, okay? So a slope field is a graphical representation of every possible general solution to a single differential equation, okay? So you should be given a worksheet that's got three differential equations on it, and then also 3 different graphs that looks just like a bunch of dots, okay? So I'm going to go through one of these with you. You're going to try the other 2 on your own, and you're going to eventually figure out how this works, okay? So to graph a slope field, okay, what I do is I recognize dy dx is equal to x. This is telling me that for any point on this entire coordinate plane, for any point, my slope is always equal to whatever my x value is. I'm going to repeat that one more time. Because I have dy dx is equal to x, my slope for this particular differential equation, my slope is always equal to whatever my x value is. So for example, at the origin, what is your x value? 0. So that means I have a slope of 0 here. But just to show that it's only at that one particular point, I'm going to draw a little horizontal line just right there. Okay? Well then, if my slope of 0, if this has a slope of 0, well right here at the point 0, 1, my x value is still 0, so I still have a slope of 0. And that's going to be true all the way along the y-axis, that you have a slope of 0. Oh, I forgot to tell you, on this worksheet, it might be helpful if you use either a ruler or some form of a straight edge. I will probably use that on here as well to make my life a little bit easier to draw these lines, because you're going to be drawing a lot of little lines. And so it's helpful if you have them kind of look like they're somewhat, straight. So now let's look at some other points. So let's look at the point 1, 0. Well, at this point 1, 0, my x value is 1. So that means just at that point my slope would be a 1. So I would draw just a little line, boop, like that with a slope of 1. I'm using I know you can't tell because I'm making a video here, but I'm using a straight edge that's lining up lines like along the line y has like a slope of 1 here, so I can make a nice pretty line. Okay. So that's the slope at this point. But what about the slope at 2, 0? Well, remember, my slope is always whatever my x value is. Well, now my x value is positive 2. So now I'm going to draw a slope a little bit steeper than the last one, like so. So now I have a slope of 2. Okay? So then over here, I'm going to have a slope of, so this is the point 3, 0. So I have a slope of 3. So I'm going to go all the way up and have a line that's even steeper than before. And then if I go over here, the line y, so 4, 0, my slope is now 4. Again, make it even more steep. So 1, 2, 2. Actually, I'm going to kind of have to eyeball this one because my ruler isn't quite long enough, but it's still slightly steeper than the last one. So because my x value is increasing as I go, I'm I'll clean that up just a hair bit. There we go. Because my x value is increasing as I go to the right, my slope is increasing as well. Okay, so that's just this quadrant. Let's go, or that's along the positive x-axis. Let's look at the negative x-axis. This is a point, -1, 0. Well, my x value is -1, so that means my slope is -1. So I'm going to draw a line with a slope of -1. I go over an x value. Now my x value is -2. So draw a line with a slope of -2. Now my slope is -3. And then I've got a slope of -4. Ish. Boom, right there. Okay? Do you guys see kind of the general pattern here? Now, the nice thing is, you'll notice that all the lines here, or all the slopes here were 0 because my x value is 0. So all the slopes here are going to be 1 because my x value is 1. All the slopes here is 2, 3, 4. -1, -2, -3, -4. So now I'm going to go ahead and fill all of these in. You might want to pause the video because I'm actually going to pause it, fill it in, and then just come right back. So that way you guys have seen the end result. Let me draw another one real quick. So slope of 1 right here. So 1, slope of 1, slope of 1, slope of 1. Makes sense? Here I want a slope of 2. So 2, 2, 2, and 2. Make sense? All right, so I'm going to go ahead and finish this out. Push pause, you finish it, and then come back. So I've got the entire slope field drawn for this. And so now you're thinking like, okay, great. I have this giant like field of little bitty lines. Great. So now what I want us to do is I want to go ahead, we're going to solve this equation. Now I want you on your worksheet to draw all 3 slope fields. Okay, following the same process of whatever the rule is. So again, I think the next one is going to be dy dx equals y. So then all of your y values are your slopes. The very bottom one is dy dx is equal to -x over y. You're going to have to plug in for each point an x and a y value and then look at your slope at each point. Okay. So then for this one, back to dy dx equals x, let's go ahead and solve for the general solution here. So again, using our rule of you got to keep them separated, I'm going to have dy is equal to x dx, because I just multiplied dx on the other side. And then I'm going to integrate both sides. And so I have y is equal to x squared over 2 plus c. This is my general solution. Well, if you look at your slope field, okay, if you look at your slope field, let's say I picked this point right here as my initial condition. So if this point is my initial condition, what's happening is that I would plug in 0, 0 here and solve for c. Okay, let's just say that I did that here. Because I wanted to have a different point later. That's okay. So if initial condition, I can spell. So 0 equals 0 squared over 2 plus c. c is equal to 0. Okay? So then you would have y is equal to x squared over 2 as your solution, as your particular solution. So then you just sketch the curve y equals x squared over 2. Because if you notice, all of these kind of look like a parabola, okay? So 0, 0 is my initial condition. Normally when I'm plotting a parabola, I go over 1 up 2, but now I'm going to go over 1 up a half, and then over 2 up. Normally I go over 2 up 4, but I'm going to go up 2 instead. So now my initial condition, and it's going to follow the curve of these lines that you have drawn. Okay, so that purple curve, actually let's make that a different color here, maybe. There you go. That is your particular solution only when your initial condition is 0, 0. If I change my initial condition to anywhere else along any point along this entire slope field, then that's going to shift this up, down, left, and right, or wherever, okay, depending on what your value of C is, okay? So you are going to finish out this worksheet, okay, on your own. You are going to draw the rest of your slope fields if you haven't already. And then at the end, you are going to go back. I'm going to go to, I think this is on the worksheet. I hope that it is, okay? Go back to the differential equations from the slope fields we drew earlier and solve for the particular solution given the following initial conditions. So these are the three conditions. This is the condition for problem number 1, condition for problem number 2, condition for problem number 3. Sketch the solution curve representing the solution that you found. Okay, so just like I did on that dy dx is equal to x, I plugged in the point that I was given and then I drew the curve on the graph. I want you guys to do the exact same thing. Okay, so you are going to do that for the remainder of class or whatever else I have planned for today. If you have any questions about slope fields, Prof. Rob Bob, Sal Khan on Khan Academy, and CalcChat/CalcView. All of those are great resources. I will also have the filled-in version of this worksheet posted on Canvas, just like I normally do. So go ahead and do that, and you will be good to go.